All right, you guys, we're going to learn about volcanoes. Now, for the exam, I don't want you guys stressing out. I'll just tell you right now, really the main points about volcanoes that you're going to get on the exam are going to be what's covered in that in-class assignment. Typically, I don't ask any other questions, but if I do, it's going to be something very small. So mostly you get to sit back, relax. This will also help you review the igneous rock lecture. So enjoy. This stuff is really, really neat. If I could go back in time, I think I'd become a volcanologist. All right, so if you guys remember before from the igneous rock chapter, we talked a little bit about intrusive igneous rocks, rocks that cool beneath the Earth's surface, and extrusive igneous rocks, rocks that cool at or near the Earth's surface. And extrusive igneous rocks are created when magma makes it to the surface or near the surface and flows out as lava. Now, if you remember the textural difference, lava cools pretty darn rapidly because the surface of the Earth is pretty cold compared to the inside of the Earth. And so usually we're going to have some very fine-grained or maybe even glassy textures. Now, we know a whole lot about volcanoes because they're right here at the surface, and we can go in and sample them. We can sample them when they're erupting. We can sample extinct volcanoes. We can see long histories. So we really know a lot about volcanoes. All right, now you guys, again, don't write this down. It's not important, but sometimes people get some names mixed up. If I asked you to draw a typical volcano, you'd probably draw me a volcano like Mount Fuji in Japan. We're going to learn that's just called a stratovolcano. And you'd make the little hole at the top where the lava comes out, and that's a crater. Now, if you've ever been to Crater Lake up on the Oregon-California border, that's actually not named correctly. That hole in the ground is so big that that's actually a caldera. And so if a volcano has a really large hole at the top, or it doesn't have to be at the top, but a hole towards the top, and it's more than 1 kilometer across, then it's a caldera. If it's less than 1 kilometer across, it's just a crater. So when we start using some of these terms, I just want you to kind of understand. All right, so the type of volcano that we have formed is strongly influenced by the silica content of the lava. Now, if you remember back from the igneous rock chapter, we did talk about silicic or felsic composition, intermediate composition, and mafic composition. Now, felsic or silicic silica content is very high silica content, and lavas with a very high silica content tend to be thick and pasty. Okay, we call that low viscosity. Okay, I always used to get viscosity messed up. So when something's viscous, it's thick and pasty, and when something's low viscosity, it's thin and runny. And basically the rhyolite type lavas are thick and pasty, and they actually are lower in temperature than my more mafic type lavas. Okay, my intermediate are intermediate in thickness and intermediate in temperature, and that would be like an andesitic lava. And then my basaltic lava. Remember, basalt is the most common igneous rock at the Earth's surface. That is actually very hot, but pretty thin and runny. And so the structure that we have built will really kind of show us, these differences. We're also going to find out that the thicker and pastier the lava is, a high silica content lava, the more explosive, the more dangerous it is. Okay, so if you're going to become a volcanologist, please study black volcanoes or basaltic volcanoes. They're much less likely to kill you. All right, you guys, in this weekly folder, I have scanned something called the V's of Volcanology. Now, we put this together for some pretty smart junior high school students, so don't be scared of this packet. It's pretty easy, and if you follow along, it just kind of tells you how we determine what type of a volcanic structure is built. Now, the volume of the lava matters. You guys, to make a big volcano, you have to have a large amount of lava. So a high volume of lava would make a big volcano. A small volume of lava would make a small volcano. All right, the amount of gases, we'll talk about it. Sometimes lava can be gassy, have bad gas, or it can be kind of flat or not have bad gas. And we'll talk a little bit about some of the different things that happen. How thick and pasty, we already talked a little bit about this. Cool lava is thick and pasty. It's a high silica content lava. And the hot lava, the black lava, tends to be thin and runny. But that's mainly not because it's hot, but because it's relatively low in silica content. And when a lava is low in silica content, we call it mafic lava. When a lava is high in silica content, we call it silicic or felsic lava. All right, so we're ready to start talking. Now you guys, again, review. This is all good for you. Basalt. Basalt, I said again, the most common igneous rock at the Earth's surface. It's the black rock that makes up the big island of Hawaii, all the Hawaiian islands, in fact. It tops Table Mountain over in Oroville. So again, low silica content. It's still made up of silicate minerals, but it's made up of those ones that have tons of iron and magnesium holding them together. Things like olivine and the augite or pyroxene. Now remember, if you come across basalt and you look at it under pretty good magnification, there is one light colored mineral that you can find in there, and that's that naughty calcium-rich plagioclase feldspar that forms at a much higher temperature than any of the other felsic or silicic minerals, but again, dominated by the dark, heavy, dense minerals, high in iron and magnesium, and therefore low in silica. Now, basaltic is typically black. Sometimes it's dark and gray in color. All right, andesite. Andesite is named after the Andes volcanic mountain chain. The Cascades is also made up of andesite. It's gray in color typically. Sometimes it weathers a little bit green, but gray. If you see gray lava or gray ash, it's probably from an andesitic volcano. And remember, it's got all of those kind of intermediate temperature silicate minerals in it. So it's an intermediate temperature, it's an intermediate thickness. Okay, and these are pretty dangerous too. People die studying these volcanoes. All right, now we have been very fortunate that a rhyolitic volcano has not erupted at its full potential in our lifetime, but Yellowstone is a rhyolitic volcano, and 640,000 years ago it erupted so violently that it would basically make most of the United States uninhabitable if it did that today. Now rhyolite is full of those light, low temperature silicate minerals like quartz and case bar, potassium feldspar, the micas, etc. And it's typically pink in color, the stuff from Yellowstone and the stuff from actually near Mammoth Mountain, which is also a pink volcano. They tend to be pink in color, and then some of the other ones tend to be creamy in color. And again, it's just, does it have that potassium feldspar in it or not? And the potassium feldspar is that pink mineral we often see that's very low temperature and high in silica content. Okay, now these tend to be really, really dangerous, really, really deadly. All right, now you guys, again, what's the good news? The good news is that most volcanoes on our Earth's surface are basaltic, okay? And you know, you can actually, if you know what you're doing, you can stand very close to a basaltic volcano when it's erupting and be in absolutely no danger. So if you guys get a chance to see any of those TV shows, the Discovery Channel, they often show geologists, volcanologists, running around on active lava flows. Believe me, they are basaltic. You do not run around on an active andesitic or Mount St. Helens type volcano. And you know, Yellowstone is not active like it could be. And so you, again, if Yellowstone was blowing up big time, you would not be anywhere near. In fact, you would be probably within 1,000 miles of Yellowstone if it really blew its top. All right, let's first talk about black lava. Okay, and remember, black lava is full of the dark igneous minerals, and it's low in silica because it's high in iron and magnesium. It's high temperature, maybe 12 or 1300 degrees Celsius, and it's thin and runny relative to our other lavas that we're going to talk about. Now, thin and runny type lava is, again, it creates these structures that are not all that dangerous, that you could be kind of close by and watching, but again, you guys have to know what you're doing. Shield volcano, the Hawaiian island chain are shield volcanoes, as are the Galapagos, and we even get shield volcanoes on land, so we'll talk about that. Okay, cinder cones, these are really, really neat, and I will show you guys these. Okay, lava flows, we're actually going to learn some foreign words. We're going to learn some Hawaiian sooner than later, names like Pahoehoe and A'a. Now, the Inuit people, or kind of Eskimo people, have hundreds of words to describe snow. Okay, and the Hawaiians have hundreds of words to describe black lava flows. So we are just going to be learning the two main ones. Flood basalts. Now, again, flood basalts have not happened in our lifetime, but we're really not all that far from sites where flood basalts happened in the past. So we'll talk about those. And then pillow lavas. Pillow lavas are black lava that erupts underwater, and it's really neat. All right, shield volcanoes. Shield volcanoes are volcanoes like the Big Island, Hawaii. Now, the Big Island, Hawaii is really, really impressive. It built up from the bottom of the Pacific Ocean floor, like, I don't know, 20,000, 18,000 feet below the sea surface. And it sticks up about 14,000 plus feet. And you know what? It is actually the biggest mountain on Earth, except we measure things from sea level and not from their base. So it is amazing. Now, it is made of that thin, runny basaltic lava. And so the lava comes out of the caldera, the craters, and it runs really far because it's thin and runny. And so what this does is this makes a low, broad, shield-shaped volcano. Okay, and it's built up layer after layer after layer of this dark, runny lava. Now, if you're a volcanologist who studies these volcanoes and you know what you're doing, even if Hawaii's having its worst eruption ever, you can still be pretty close to it because this is the black lava. It's not as dangerous. The thin, runny lava allows the gases to escape so they don't blow up explosively. All right, and the biggest volcano on Earth is I think the Big Island of Hawaii. I'm not 100% sure, but I know the biggest volcano in our solar system is Olympus Mons, and Olympus Mons on Mars is a giant shield volcano. All right, again, flow after flow of this runny stuff, and again, generally not very dangerous if you know what you're doing. They do evacuate people because, you know, people are stupid. But personally, I know no geologists or volcanologists who've died on black volcanoes. They've all died on gray volcanoes. There are a lot of idiots who die on black volcanoes, and I don't want you guys to be one of them. So we're going to teach you a little bit about what not to do. There are two distinctive types of basaltic lava flows on Hawaii, and I'll teach you guys about those and show you pictures here in a bit. And again, Mauna Loa and Mauna Kea on the Big Island of Hawaii are really great examples of shield volcanoes. Now, after this exam, we're going to start right in on plate tectonics, and we're going to talk about specifically how actually the Hawaiian Islands have nothing to do with plate tectonics, but they actually support plate tectonics. And these are formed by hot spots. It's like a single candle of really hot magma coming up from a very deep source, probably pretty close to the core. And so the plate, that's the Pacific plate, and we're going to talk about plates move. The Pacific plate moves over this kind of hot candle-like thing, and that candle burns a path. And so we can actually follow that path and see how the plates move. Now, the only island in the Hawaiian island chain that's active right now is Hawaii, but actually there's a brand new island forming to the southeast of Hawaii, and its name is Lohi, and I think I'll show you guys a picture later on. All right, now here is an Icelandic shield volcano. So shield volcanoes can also occur on land. These are a little smaller, but look at that low, broad dome. And again, runny, thin lava runs really far. Think about milkshakes. If you had the thickest milkshake in the world and you dumped it over on a desk, it may actually keep the shape of the cup for a while because it's so thick and pasty. But if you take a pretty runny milkshake and you flip it over on the desk, it's going to run out because it's thin and runny and not stick up tall like the cup. And it's kind of like that. Thin and runny makes these low volcanoes. All right, I like cinder cones, and I believe it was in the 40s that Paracutin in Mexico erupted. A farmer was just out in his field with his corn, and he saw smoke, and he ran over, and there's a crack in the earth. And within a couple of years, there was a 1,500-foot cinder cone. And after the cinder cone erupted, there was a lava flow that went into the town and covered it. And there's pretty famous pictures. I'd be very surprised if not every single textbook probably for earth science and geology probably has a picture of this. And if you guys do get to Mexico, go visit Mexico City, try to go see this Paracutin. These are short-lived. When they're over, they're completely over. So it's pretty safe, volcano-wise, to climb a cinder cone. Now, this is from basalt again, but this is from basalt with bad gas. And it's kind of like if you pop popcorn and you take the little kind of container lid thing off that makes it kind of funnel into your bowl and it kind of pops everywhere. And that's kind of what happens with a cinder cone. So very, very gaseous lava, boom, 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 pop, pop, pop. It's black lava. And that makes this rock called scoria. So it's basalt with holes in it. Now, that actually needs to be changed. That should be a much steeper angle right there. That should be 40 degrees, 35 degrees. Remember that if you guys think about popcorn, if you're popping popcorn in a hot air popper, the popcorn's very angular and it's got these little pieces that can kind of hook together. Think if you tried to make a pyramid out of marbles, the marbles would probably just fall. You'd never be able to make a very high pyramid. But if something is angular sides, it kind of hooks into each other and you can make something very steep. So these things are very steep. All right, this is one of the best cinder cones ever. And this is called cinder cone, which, you know, not a very inventive name. And it's part of Lec7 Volcanic National Park. And it's up in the kind of the northern corner of it. And it's just spectacular. Luckily, it's been preserved. Most cinder cones are mined. Again, cinder block, they use it for roads, they use it for landscaping material, building material. And the reason why they're so popular for mining or quarrying is because it's all loose. Okay, that's not glued together. It's all loose. It's just like all that popcorn stuck together, but no caramel to hold it together. It's all loose. And so when you hike up one of these, you might say, oh, look at that big, you know, nice path up the side of it. It's a workout because it's like a Stairmaster. You take one step and you slide. You take one step and you slide, and they're pretty steep. Now this one's about 800 feet high, and yeah, you can't really see in this picture, but I've got a couple of my students up there at the top. So it's just really spectacular. And if you guys ever get a chance, you should go climb this one because it's absolutely pristine. One thing is we'll ask you to stay on the path because if you run down the sides of it, you're going to cause erosion and it won't be beautiful and pristine. All right, these are small in size. You know, not most of them are much smaller actually than 1,500 feet or 500 meters, but that's about the biggest they can get, about 1,500 feet. You often see them in groups. I'll show you guys some more pictures. Now, when we talk about plate tectonics, we're going to talk about when plates pull apart, and when plates pull apart, we call that divergent. And the type of faulting, we'll talk again about that next section. And these are kind of tied in with that type of plate motion. Okay, they're usually short-lived. You know, they don't last very many years, and they're easily eroded because they're not glued together. Now, after you get rid of all the gas, sometimes you still have lava. And if that lava that's now kind of flat, you know, comes to the surface, it doesn't come out the crater. Okay, it comes out, it just seeps out the sides because it's not glued together. So I'll show you guys pictures of that too. It's pretty cool. All right, now here is an active volcano at the top, an active cinder cone going. See the little person, jeans and a t-shirt, okay? And that person is totally safe. They know what they're doing. They're completely safe. Now, they may have earplugs in because boom, boom, pop might hurt your ears. But if this was any other type of volcano, you know, any type of lava, they would not be standing that close. Now, on the bottom picture, this is off along Highway 40 in Arizona. And you can actually see a beautiful cinder cone there. It's been a little bit oxidized. Remember, if you've got a lot of iron in you, you can get a little rusted. And you guys can see the lava flow, and the lava flow, it goes right, you know, the road goes across it because it predates the road, but you can see it just came right out of the bottom. It did not come out of the crater, just seeped right out of the sides. All right, here's my favorite place on Earth, the eastern side of the Sierra. And we often climb cinder cones when I take classes there. Now you can see the cinder cone that we're actually on, or I'm taking this picture from, is a little older because it is vegetated. And you can see a series of other cinder cones and a few, there's a lava flow or two coming out of them. And they're all along this eastern side. And they're also along or they're on the eastern side of the Sierra, but this is the western side of the Basin and Range Province because the Basin and Range Province has those normal faults and those boundaries that are pulling apart. And so we actually find them on both sides of this spectacular valley. So this is not far from Mono Lake and Mammoth Mountain. All right, our Hawaiian vocabulary lesson. Pahoehoe lava flows are thin and runny. And so when they cool, they have this ropey appearance. Now the surface cools, and the surface cooling causes that, like a skin to form, and then as the skin moves, because the lava beneath it's still flowing, that's where you get that ropey appearance. Now that skin forms an insulating layer, so the lava inside still remains hot and it keeps flowing. Now, you guys, if you go to the Big Island of Hawaii and you do what everybody does, at 5:30 the guards go home where the lava's running into the ocean, and you jump the fence and you go run out there. Be careful, because if you run onto too fresh of lava like this, you can fall through, and people fall through and die. It's, pretty hot. If your shoes are smoking, you really shouldn't be doing that if you don't know what you're doing. All right, so we're going to talk about this because this type of a lava flow, actually, think about it. If we form a pretty good skin on there, and then all the lava runs through, we're actually left with a tube at the end. And once this whole system cools down and the lava's not flowing anymore, you can actually hike through these tubes. And I'll tell you about a place you can go nearby, somewhat nearby. All right, here's the other type, an ah. Yeah, that's a word, ah. And this is what I call a hot burning rubble pile. The gases have been removed. It's not running as nicely. It surges forward. It moves slowly. These people standing right here are perfectly safe. It kind of falls over and surges forward, and it's just really, really hot. And if your house is in the way, you're kind of out of luck. Now the Hawaiians are, they worship Pele, or they respect Pele, the goddess of fire, and they don't seem to try to control the lava like some other places do. Iceland, for instance, if this was Iceland and that lava flow was approaching a harbor that was really important, they'd be out there with big hoses and water cannons spraying water on the flow, cooling that lava front, and directing and deflecting the lava elsewhere. But I've never seen that done on Hawaii, and I think it's because of the respect for Pele. So here we are side by side, an big chunky rubble flow, and a pahoehoe flow. Now once these cool, it's much easier to walk on a pahoehoe flow. Flow is sharp and jagged, and if you don't fall down and cut yourself pretty badly or twist an ankle, you're going to wear out the soles of your hiking boots really fast on the flow. Okay, the pahoehoe is much smoother. All right, flood basalts. Now, we haven't had any recent flood basalts, but if you guys have ever been up to the Columbia River Gorge, right at the border of Washington State and Oregon State, the Columbia River makes the boundary between the two states. And the Columbia River has been river's downcut, through some very old, or not that old actually geologically, lava flows. Okay, and now these were lava flows that are pretty amazing. This is basalt at its runniest. It's so runny, in fact, it doesn't even make like a volcano. And what happens is you have a fissure, a crack would open up, and huge volumes of lava would run. And these can cover thousands of square miles. It's amazing. And not only covering thousands of square miles, but also up to, more than a mile thick. That's what makes it so absolutely amazing. So just flow after flow after flow. And so when we talked about layered rocks, most layered rocks are sedimentary. Here's an example of volcanic rock that's layered, because flow after flow after flow. Now, if something like this opened up in the United States, it would be pretty devastating. I'm not saying that, but it's not explosive. It's just the fact that it's so runny, it would cover huge areas, and those areas would be, non-livable for quite a while. All right, and here's just another shot of the Columbia River Gorge, and flow after flow after flow of lava that flowed, 20 plus million years ago. All right, on my Eastern Sierra trip that I keep kind of hinting about how much I love it, I usually take the students to the Devil's Post Pile. And the Devil's Post Pile can be found at the end of the road past Mammoth Mountain. And obviously, when Mammoth Mountain is going full blast for ski season, you can't get to Devil's Post Pile. We only go there in the summer when the road is open. Now, the Devil's Post Pile was created when basaltic lava flowed and cooled. And when it cooled, it started to contract. Things that cool typically contract. And it actually contracts in a pretty cool form, a polygon. And in this case, it's mostly a hexagon, but although that you can find 5- and 7-sided and 8-sided, but typically most of them will be a 6-sided figure, and it's called columnar jointing. Okay, now here's the Devil's Postpile. I typically take students up to the top. If you look at the bottom right-hand picture, you take them to the top first, and what you see is that top left-hand picture. Those are pretty good size post piles. And what they are is, this lava flow was several hundred feet thick, and it's cooled, and it cools from top down, I think. And what happens is you get these things. It's almost like having kind of those angular pencils all stacked on edge. And luckily a glacier went over the top on that top left picture and smoothed the top. So you just have this beautiful picture. And then if you kind of look at the bottom right picture, you can see what they look like, on their side view. So really, really neat. I love that place. And you can go for pretty inexpensive. And it's in California, not too far away. Now you get the same type of columnar jointing in all of the lava types. Here it is in the pink lava on that same trip. I go to the Owens River Gorge, and we go to kind of talk about the Mammoth Mountain area. About 760,000 years ago, it had a cataclysmic eruption. You find the ash from this eruption all the way to Nebraska. We watch Mammoth Mountain and Yellowstone very closely. These are those rhyolitic pink volcanoes that are so deadly. And they're both active still, but luckily all of the volcanic activity has been on a much smaller scale. But here you can see it in the pink lava. And up by Mount St. Helens, I found this. You can see the columnar jointing in the gray lava. So it does happen in all the lava types. It's just that Devil's Postpile is probably, I think, it's one of the most wonderful places in California that everybody should go see. Okay, in the fall, I take that field trip. You guys can go, 3-day trip. All right, remember the Pahoehoe flow and the insulating skin, and the insulating skin can get pretty thick, and that lava inside is insulated and it's hot and it runs out. And if that volcanic system stops, all the lava runs out, a lot of times you're left with these lava tubes. Now, Lava Beds National Park up in the, California, Oregon border, it's on California side, up near Klamath. It's really spectacular. Lots of great lava tubes like this one. But we have one a little closer, and I'll show you guys that. It's up in the Lec7 forest, okay? And it's called Subway Cave, and it's not from Subways, and it's not a cave. It's actually a lava tube. So the lava ran out. And you can see about waist level, that was the height of the last lava flow that went through there. Okay, and they can be huge. There's some of them up at lava beds that you can drive an 18-wheeler through, and then there's other ones that you have to crawl on your hands and knees or even belly crawl to get through. And you get this from the Pahoehoe flow, so basalt. Now this is Subway Cave out in the Lassen National Forest, and you usually find these things because part of the roof collapses, and you can find your way in. If you're up near Redding in the summer and you're just hotter than heck, go down here. These lava tubes stay nice and cool. Okay, and look at the sides. It kind of looks like, they've been plastered, but it's all from the lava flows. Now, a lot of times when we go into these, we wear hard helmets because when the lava drips off the surface, or the roof, it forms what we call lava sickles, shark tooth lava sickles, and they'll cut your head if you're not careful where you're walking. Okay, yeah, there are roof collapse. This one's pretty safe here, because it's kind of a drier area. But this one, Subway Cave, I do believe is safe enough to take children into. Okay, so the lava tubes are pretty cool. Now, pillow basalts. Great pillow basalt site would be kind of near Port San Luis, near Morro Rock is down near San Luis Obispo, Cal Poly San Luis Obispo. But we actually have some up the road from us, up Highway 80, and I'll show you guys those. They're a little bit metamorphosed. Now, when basalt erupts underwater, the outside, this 1200 degrees Celsius lava hits that 2 degrees Celsius, or just cold ocean water. And it cools really fast, and it kind of forms a crust, and then it causes these in cross-section, they look like pillows, and that's why they're buns. But this like sausage, you can see kind of in front of the guy who's standing there, on its side, the sausage, kind of fallen over sausage. Now, I will put a link to a really great YouTube video taken, you can go to Hawaii and actually, if you have, again, the right connections or you pay a company, you can go scuba diving right off the coast where the lava's running into the water. But that's not what you want to see. You want to see lava vents that are underwater. And when the lava erupts underwater, it forms these amazing pillows. So be sure to watch that video because then you'll understand what's going on. Now, a lot of these are formed at the mid-ocean ridge, and we're going to talk more about that. But you can tell, the depth at which they're formed and things like that. But these are really spectacular, the pillow basalts. All right, now this is up between Applegate and Meadow Vista, right off the Highway 80 is just right there. And these are slightly metamorphosed, so they've been they're a little green. The black minerals turn a little green. So we call them pillow greenstones, but they're pillow basalts that have been scraped off onto the North American continent because they're formed deep in the ocean. So the scraping off act has actually metamorphosed them, but you can still see the pillow structure. It's pretty cool. All right, and here's a great close-up shot, world famous tectonicist down there on the bottom, Tanya Atwater, pointing out the rind. You can kind of see, you guys see the pillow she's touching? Look around the outside, there's a black kind of surface to it, and that's where it contacted the water. Now the inside stuff is just typical basalt, but you can really see in cross-section that pillow look to it. But on the other view, it would look kind of like falling over sausages, like you can see in that upper left-hand fourth picture in that upper left-hand side of it. So pillow basalts are really cool. All right, so let's go to the more dangerous ones. Remember, if you don't know what you're doing, stay away. And in fact, mostly they'll keep you away when a gray volcano or if a pink volcano is very active. Higher silica content. Higher silica content means thick and pasty. Thick and pasty lava means more dangerous. Okay, why? It's kind of like a pipe bomb. Pipe bombs are dangerous because you cap the ends of the pipe and you contain the explosion. So the explosion can't expand, and so it actually does expand anyways, but it expands super explosively, and that's kind of what happens. The thick pasty lava, the gases can't escape, and if they can't escape, they're going to just blow, and so they blow up, and it makes it pretty deadly. Now we're going to talk about a Mount St. Helens or a Mount Fuji type volcano called a composite or a stratovolcano. We're going to talk about lava domes. Mount Lassen is actually the world's largest lava dome. And then we're going to talk about the big bad guys, the giant calderas. And again, we're lucky that we haven't had one erupt cataclysmically in our time. All right, stratovolcanoes. Most stratovolcanoes, strata means layer, they are layered, we'll take a look, are found around the Pacific Ocean rim. And that's because we've got plates crashing together surrounding the Pacific Ocean ring, and specifically an oceanic plate is involved. And when it's involved, it actually melts and creates this gray lava. And so these are kind of your classic volcanoes. If I asked a bunch of kids and went to visit a junior high, say, hey, draw me a volcano, probably 90% of them or 99% of them would draw me a Mount Fuji type volcano. Okay, so they're pretty high, they're wide, they're big, they're pretty large volume. All right, this is Mount Rainier, and Mount Rainier is potentially one of the most dangerous natural hazards that we have here in the United States. It is volcanically active. It is still active. This is part of the Cascades, and the Cascades are still active. And the reason it's so dangerous is that ice. It has so much ice on it that all you need is a small steam eruption. And in fact, in the foreground, you guys can see a little bit of a bare part, and it looks kind of like gravelly. That is where, if we had a small steam eruption, the water would melt, it would move down slope rapidly and carry all that loose material down and create, we're going to learn another foreign word, but it would create a volcanic mud flow that would be very, very dangerous to people living downstream. Now, a lot of people live, this is Pacific Northwest, this is Washington State. Some of these past lava flows have gone all the way to Puget Sound, or not lava flows, but mud flows. Again, 50,000 years ago, not today, but it could happen at any time. Okay. All right, so what happens with a composite cone? Now, you guys are too young to have lived through Mount St. Helens, but it was pretty exciting. I was a kid and Mount St. Helens blew. And you might say, well, Mount St. Helens isn't scary anymore. That's because these volcanoes go through very eruptive periods and then they go through more quiet periods. And in fact, in 2004, Mount St. Helens did erupt again enough that it closed the whole park. Okay. And so you just kind of vary between big eruptions and then quiet times, or even times when you just have lava. So you'll get the loose material, the pyroclastic material, but then later on you'll get the glue or the lava that holds it together. All right, so here's just a shot that these take millions of years to form. They get destroyed pretty quick. Mount St. Helens was beautiful and symmetrical. I'll show you guys, I think, a picture. And then, boom, it blew up in 1980, and then it wasn't beautiful and symmetrical. But it's going to build itself probably beautiful and symmetrical again, and then, boom, blow up pretty violently. So again, it's flow after flow. There's pyroclastic material, the loose ash, rocks, etc. And then a lava flow will come over and glue it together. Because it does have this glue holding it together, these are a lot harder to erode than a cinder cone. Okay. Now here is Mount St. Helens in 1980. Okay, and it's beautiful. It's symmetrical. And then here it is. Actually, this is in 2004, right after they opened up the park when it was closed from being active, and that's still active. You guys can see, the little bit of gases and ash and steam coming out of it. And when it erupted in 1980, again, look at all the links I put up there for you. You can actually watch it erupt. It was really violent. And in fact, a lot more people died. Some people chose not to leave, and other people just didn't realize it was going to blow sideways, and it blew sideways versus straight up in the air. And if you guys ever get a chance to go up there, enter on the west side. I mean, you can go in the east side too, but go in on the west side and you can go to Johnson Observatory in Johnson Ridge, and that's where Dave Johnson died. He was the USGS geologist sitting watching that. And kind of weird is he changed places with a guy that I went to school with, Harry Glicken. So Harry Glicken lived and Dave Johnson died. But and it's your time, it's your time. Harry Glicken died not too long later on Mount Unzen in Japan, another gray volcano. Okay, so yeah, if you study gray volcanoes as a volcanologist and you're really actively studying active volcanoes, your life expectancy isn't so great. Kind of sad. Study black volcanoes. All right, now they're very violent. That earlier shot I showed you guys, that's 25 years after the eruption, and it still looks kind of, wiped out. Now, a pyroclastic flow is a glowing avalanche, and again, I've got pictures or video of pyroclastic flows in that folder for you. And they're deadly, and they move so fast, and that's actually what killed Harry Glicken. He and the Kraft couple, the French volcanologists, cinematographers, went on Mount Unzen. They went up a stream valley, and they wanted to capture the video of this pyroclastic flow, also called a Nuit Ardente, coming down, and they were incinerated. Now the lahar, that's that volcanic mud flow. That's when either the gases or the eruption itself melts ice or snow on the sides of the volcano, or else it rains when the volcano is erupting, and that will move all that loose material downhill. And remember, it's pretty steep, and you got a long way to go. Picks up a lot of momentum and can kill people really far away. All right, here's just kind of a shot. What goes up must come down. That's why we don't shoot guns up and straight up in the air to celebrate New Year's. Not a very wise idea, because the bullet's going to come down. And so the loose material, gets shot up, ash, gases, rocks even. And when that energy starts to dissipate, what goes up must come down, and it goes shooting down the sides of the volcano very violently. Okay, here's a still shot of these pyroclastic flows, and they go pretty far out. And so you might say, well, why are they evacuating people, in a 20-mile radius or more? And that's because these pyroclastic flows, or even the lahar, can travel out really, really far. Okay, lahars are volcanic mud flows that flow down, and again, they can travel 50 plus miles and kill people if you're not aware of what's going on. Now, sometimes when volcanoes erupt, they make their own weather systems because, water vapor's coming out, and so is ash, and the ash is particulate matter, and the water vapor cools and condenses around the ash and falls out. and or else some ice and snow melts and it just moves down slope. And it's not like being hit by water, it's like being hit by a freight train. The stuff is dense. Okay, now this is a sad picture, you guys. Central America, there's 20,000 dead people under this because a volcano about 15 miles away had a lahar form, and in the third world countries, a lot of times there's no warning system. Now, if you lived in the Pacific Northwest, sirens would go off, and you guys have been through a whole bunch of evacuation practices, and you'd all be on that little island in the center. Okay, that's higher elevation. They take you uphill for a reason. Now, you'd be cold, wet, scared. Everything would be gone, but you'd still have your lives. So, you got to think about these things. And as a first world country or developed country, isn't it our duty to kind of help these developing countries to watch out for these naturally occurring disasters? I think so. All right, now you may say, well, lahars, I've got nothing to do with lahars. I've never seen a lahar. Oh yeah, you have, especially if you live anywhere near the Rockland campus. This is taken on Sierra College Boulevard, and this is, if you go from this Rockland campus towards Lincoln, you go down into the Loomis Basin, and then you start climbing uphill. And you can also see this if you go on the other side of Sierra College Boulevard towards Douglas. And what you see is, you see those rounded boulders? That's a stream bed. And then look above it. You see something much, much more, that's an ancient stream bed. This was a stream 5 to 19 million years ago. And, the lahars follow streams. They're like water, very thick water, but fluid. And so they go the path of least resistance, just like water would. And so you can actually see that. It's, pinkish gray, concretey looking stuff up above it. And you can see flow after flow of these. So 5 to 19 million years ago, the whole western foothills of the Sierra in our region would be a horrible place to live. Those volcanoes aren't there today, so we're okay, but in the past they were, and you guys have probably seen lahars, is my point. All right, Mount Lassen is the world's largest plug dome. Also, hey, if you guys on your bucket list, you want to climb a Cascade volcano, this is the easiest one to climb. You start in a parking lot at 8,500 feet and you only go up about 2,000 feet. Yeah, it's steep. You got to watch the weather. You got to be in pretty good shape. But if you really want to bag a Cascade, this is the easiest peak to climb. Now, it's not a stratovolcano. We've pretty much lost the gas, and it's kind of like if you take your toothpaste tube and you just give it a squeeze and out pops the toothpaste. It just pops up and then falls over. Now, they are associated with explosive eruptions because you gotta usually get rid of the gas first, and then that means boom boom in a big way because this is thick and pasty, so explosive boom. But once the gases are out, then you get this thick, flat lava that just comes up and falls over. All right, so you only get these formed when there's low gas content. Otherwise, you got big explosion. Now, these are rhyolitic or dacitic, which is kind of intermediate between rhyolitic and andesitic in composition. All right, they can grow out of a stratovolcano, and in fact, we have a lava dome forming right in the kind of crater in Mount St. Helens right now. And if that plug was to keep gases from coming up, it would be dangerous because, sometimes, like if you take the little cage off your champagne bottle and you're just leaving it there, it'll pop anyways. And that's because of the pressure that builds up inside the champagne bottle. And the pop of the champagne bottle would be the similar of a big eruption on Mount St. Helens. Now, these lava domes are a great source of obsidian. And in fact, Native Americans realized the importance of obsidian, and California has a lot of these glass mountains or lava domes where the Native Americans took advantage of it and made their arrowheads and knife blades and things like that. Okay, monocraters and domes, Inyo-craters and domes, great examples. Now, Mono Lake is up in the upper right-hand corner, and these are actually the Inyo domes, and they kind of look like mushrooms at the, when mushrooms are coming up after the spring rain. And Highway 395, you can kind of see running kind of down the center of this shot and the eastern side of the Sierra. And you get a little cross-section of what these look like. And just kind of imagine them like thick, pasty toothpaste coming out, and you got obsidian, and usually surrounding it you've got a little bit of the pumice because there was some gas at some point, and so you'll have pumice, and they mine obsidian, etc. from around here. All right, here's Lassen, spectacular. Now, Lassen did erupt in the early 1900s, and the people in Lassen hate Mount St. Helens because until Mount St. Helens erupted in 1980, Lassen was a super popular park because it was the only Cascade volcano to have a big eruption in the 1900s. Now, it lasted a couple of years, and in fact, right at the top, you guys can see a little bit of, in the clouds, the black, dark stuff that's sitting on top of some snow and ice up there, and that's actually part of that. And so it's a dark colored dacite. So this, is a pretty exciting place. And this park is really underutilized. You guys can go there, explore. It's really great. Go in the summer, swim in the lakes. It's beautiful. And it did have people lived out here. Again, it was ranchers and stuff. Nobody died. Dogs saved lives. Dogs barking got the ranchers up. They ran to the top of the hill to see what was going on, and any people that were still on the low grounds, they made come up, and nobody died because of dogs. Okay, so that's why I love my dog. Going to save my life next time a volcano erupts. No. But right here where we're looking is a pretty devastated area where a pyroclastic flow and a lahar at different times came down. So it still looks pretty devastated from the, I think it was 1918 to 1921 that this was active. If you guys get up there into the visitor center, there was a famous photographer there at the time who took lots of great pictures. All right, let's talk about the worst case scenario. A giant continental caldera. These are pink or cream colored. These are rhyolitic volcanoes. And luckily they don't happen all that often and have not happened in our lifetime in having a cataclysmic eruption. So you have just a huge hole in the ground. Now, we used to think the huge hole in the ground was caused because all the material that was in the magma chamber came out. But typically you just have a partial evacuation of the magma chamber. But the stuff, the rock on top collapses back down inside because it's not being supported, and that actually creates the big hole. The big hole in the ground at near Mammoth Mountain is, I don't know, 18 by 20 miles. That's a big hole. And the one at Yellowstone's a little bit bigger. It's something like 20 by 25 miles. So really, really big. All right, so we have Yellowstone, we have Long Valley. Mammoth Mountain is a younger series of volcanoes that's sitting up on the rim of the Long Valley caldera. Lots of pumice. If you guys go down in that region, you're going to see lots of pumice. If you ever ski at Mammoth Mountain, you're going to be like, oh, what's that smell? It smells like rotten eggs. What's that steam coming out of the ground? That area is still active. But the good news is since Mammoth Mountain area erupted so violently 760,000 years ago, there's been lots of volcanic eruptions, and they've all been much, much smaller scale. So maybe we're releasing any pressure, so we're not going to have a cataclysmic eruption. The other thing is both of these places are really closely monitored by geologists. So, before I take my students down on my Eastern Sierra trip, I go to the USGS site and make sure that Mammoth Mountain isn't looking scary because I'm not going to take my students into a dangerous area. All right, now there is another giant caldera in the United States. It's in New Mexico, and I'd never been there. And in fact, until a few years ago, I'd never really even heard of it. And so I made a trip out there at New Year's a couple of years ago. It's called the Vice Caldera, and it's older. It's considered. All right, so here's the Vice caldera. Again, it's a much smaller scale caldera than Long Valley caldera, where Mammoth Mountain is, and the Yellowstone caldera. They're like 20 by 25 miles for the Yellowstone and 18 by 20 miles across for Long Valley, and this is just a mile or two across. It's really not all that big, so you can actually look and look across one direction, and then here you go looking across the other direction. Now this is a really cool area. It's an elk reserve, and it's cross-country skiing and snowshoeing area, so it's pretty cool to go to even if you're not just doing the geology. All right, when you see a big hole in the ground that you think is a volcanic caldera, you got to go and look for the pink or cream ash and lava and stuff, and here it is. This is tent rocks. Now, later on, there was a basaltic lava flow that went over the top, and the basaltic is a little bit more resistant than this ash flow, and so what's happened is that you get these really strange erosional patterns, hence the dunce cap look or the wizard hat or the tent rocks. And again, here you can see that basalt at the tippy top there, giving it kind of that strange look, and then lots of the pink rhyolitic ash. And like I said, lots and lots of it. So big hole in the ground, that's a caldera, a rhyolitic caldera. This is Tent Rock. So if you guys ever get a chance to go to New Mexico out by Albuquerque and Santa Fe, you can visit these areas. They're pretty cool. I love this shot, and I love this shot because here we have cinder cone. This is Lassen area. So here's cinder cone, and straight ahead is Lassen. To the right, you have that forested shield volcano. And if you were to climb up that forested shield volcano, you could actually see Mount Shasta. Mount Shasta is a composite cone. So we've got a cinder cone, the world's largest plug dome in Lassen. We've got a continental-based shield volcano, and then, you know, in that same general area you have Mount Shasta, which is a composite cone or stratovolcano. So no excuses about, oh, you know, too far away or too expensive. You can go there pretty quick. You can camp in the summer months. It's beautiful. You can hike, and really pretty low budget. It's gorgeous. And hey, you can even hit a lava tube if you go to Subway Cave. So lots of great stuff to see here. All right, here's the slide that I actually came across that made me say, hey, you know, what's this Valles Caldera? And just remember, Valles Caldera is much smaller than Yellowstone or Long Valley. So just kind of, you know, been there, done that now, and it's kind of nice. All right, now we've been talking about features that stick up. Even a giant caldera, you've still got the sides to go up. It sticks up. Well, let's talk about a negative volcanic feature. And when the groundwater encounters the magma that's under the surface, or the lava that's closer to the surface, that groundwater flashes to steam. And when that happens, you get a big explosion. And it creates a big crater called a Mars. And so phreatomagmatic, phreato means steam, magma in contact with the magma eruption. And one of the most famous ones is Yuba Hibi crater, and this is a series of craters, but this is the big one, Yuba Hibi, in Death Valley. And so you guys, when you go to Death Valley, again, don't go in the summer months. It's awfully hot, but if you go in the spring, good time to go. Even winter's not too bad. You can actually get here. It's on a gravel road, but you don't need special four-wheel drive or anything to get to Yuba Hibi. And you should go check it out. So it's pretty cool. It's pretty neat. It's a couple hundred feet. What is it, like, it's a half a kilometer or half a mile across, and 700 feet deep or something like that. It's pretty neat. So a giant steam eruption, okay, from when the groundwater that used to be in here in the Pleistocene during the ice ages came in contact with the magma that was under here. All right, and the Inyo craters and domes, I showed you guys, these are just to the southwest of Mono Lake. We saw the domes earlier, and you can kind of see a dome peeking out on the right-hand side, but these are the craters. And again, the crater was formed when groundwater got in contact with hot rocks, or probably even the lava or magma, and went to flash to steam and just blew a huge hole out.